Hello everyone, I am Saurabh Jogrekar and today we are going to discuss integration by parts. Okay, so this is a technique which works when you have a function which you want to integrate, which happens to be the multiplication of two different types of functions. Okay, for example, if you have something like x sine x dx. Okay, so x happens to be an algebraic function and t sine x happens to be a trigonometric function. Okay, so in this case we are going to apply integration by parts and see how to compute the antiderivative of this x sine x. Okay, so before we do that, let's see the formula. Okay, so the formula for integration by parts is given by u dv equal to uv minus integral v du. Okay, so this looks like a fairly complicated formula, but we can have a quick derivation using the product rule for differentiation. Okay, let me walk you through it very quickly. So assume that u and v are functions of x. So the product rule says that d of uv, that is the multiplication of u and v, differentiated with respect to x, this is equal to u v prime, which is derivative of v, plus v u prime. Okay, and now I'm going to multiply both sides with dx. So what I get is d uv equal to u v prime dx plus v u prime dx. Okay, and now this part v prime dx, I can write it as dv because dv equal to v prime dx. V is a function of x, and u prime dx, I can write it as du u prime dx. Du equal to u prime dx. U is again a function of x. Alright, so I can write this as u dv plus v du. So d of u multiplied by v is u dv plus v du. Alright, and then I'm going to integrate both sides, and what I get is integral d of uv equal to integral u dv plus integral v du, because integration of a sum of two terms is equal to the sum of integrals, right? And then this gives me uv, integral of d of uv is just uv, right? And this is equal to integral u dv plus integral v du. Okay, and all you need to do is rearrange these terms and you will get the formula for integration by parts. Okay, so this is a very simple derivation for the formula. I'm not going into technical details of what this dv and du mean. They are called the differentials of u and v, and there are a lot more technical details to this, but we are not going to see that today. Okay, so this is just a quick derivation. All right, so let's try to apply this formula to the problem which we started with, which is integral of x sine x dx. Integral x sine x dx. Okay, so the first job you want to do is identify which part of this is u and which part of this is dv. Okay, so I'm going to say that u is equal to x and dv equal to sine x dx. Okay, now the dv is the differential, so it will contain the dx term, and u is just a function of x, so it's just a simple function. There is no dx in there. All right, now you might ask me why am I choosing u equal to x. I can very well do u equal to sine x and dv equal to x dx, but this thing is not going to work, and I'll show you why it doesn't work. But for the moment, let's start with this. Okay, we are going to start with this. Okay. All right. So u is x. So I know what is u. I know what is dv. Now I want to know what is v and what is du from these two equations. So to find out du, what I'm going to do is differentiate the first equation. I'm going to differentiate. So what I get is du over dx is equal to 1. Simple differentiation of x. And this gives me du equal to dx. Actually, it's just 1 times dx is nothing but dx. Alright? And then to find out v, what I'm going to do is integrate the second equation. So integral dv equal to integral sine x dx, which gives me v equal to minus cosine of x, because integral of sine x is minus cosine of x. Now technically, when you do the integration, you have to add a constant of integration, but we are not going to do that at this step. We will add a constant of integration at the end. Okay, so don't add a plus c at this step. All right. So now we have all the pieces of information we need to apply the formula. Okay, so let's plug in everything into the formula. So what we get is integral x sine x dx is u times v, which gives me x multiplied by minus cosine of x minus integral v du. V is minus cosine of x, and du is nothing but dx. Du is nothing but dx. Alright, so let's simplify this. This is minus x times cosine of x plus integral of cosine of x dx. And as you know, integral of cosine x is just sine x. So this gives us minus x cosine of x plus sine x, and then I'm going to add a constant of integration, which is plus c. So this is our final answer. Okay, this is the final answer. Alright, so we started with u equal to x and dv equal to sine x dx, and I told you that if you reverse the choice, that is u equal to sine x and dv equal to x dx, that's not going to work. Okay, so let's see why it does not work. Alright, let's make that choice and see what happens. Okay, I'll keep the answer as it is. Okay, so let's choose u equal to sine x and dv equal to x dx. Now once again, to be able to apply this formula, I need du, so I'm going to differentiate the first equation. Differentiate this. So I get du over dx is equal to cosine of x, which gives me du equal to cosine x dx. Okay, and to find out v, I need to integrate the second equation. So integrate dv equal to integral x dx, so that gives me v equal to x squared over 2. And as I said, we are not going to add a constant of integration at this step. Alright, so now we have all the pieces of the information. So let's try to plug everything back into the formula, and what we get is integral x sine x dx is equal to u times v, u times v. So we get sine x multiplied by x squared over 2, and then minus integral v du. V is x squared over 2, and then du is cosine x dx. Alright, so see what happened. We had a power 1 over here, x to power 1, and on the right hand side now we have x to power 2. So this second integral is actually more complicated than what we started with. Okay, so the goal of integration by parts is to reduce the complexity of the integrand. But with this choice of u and dv, we are going the reverse way. We are making it more complicated. And we still don't know what is the integral of x squared over 2 times cosine x. Okay, so that's why this choice is not going to work. Okay, so our earlier choice did give us this answer, but this thing, we don't know how to integrate this. Okay, so you might want to ask whether we want to do this type of trial and error to decide what is u and what is dv. Okay, how do you choose what is u and what is dv if I give you some random problem? Okay, the answer to that question is that we have a simple rule. It's a rule of thumb. It's called LIATE rule, L-I-A-T-E. Alright, so this is a rule of thumb which works in many cases. It does not always work, but it does work in many cases. Let's see what this rule really means. L actually stands for logarithmic function, which is nothing but ln x. Or in most general terms, you can have ln of, say, f of x. This is a logarithmic function. Okay, so all functions of this type, we are going to call them logarithmic functions. Then I is inverse trigonometric function. So these are all the functions of type sine inverse of x, cosine inverse of x, and so on and so forth. Okay, there is another notation for this. We call this arc sine of x, but it really means the same thing. I just like this sine inverse notation better than arc sine, so I'm going to use that. Okay, then algebraic, AA stands for algebraic functions. A is algebraic function. Now the exact mathematical definition of an algebraic function is somewhat complicated, and we are not going to go into the details of that, but for all practical purposes, for our purpose, algebraic functions are all the expressions which involve powers of x combined with the operations addition, subtraction, multiplication, and division. So all functions which you get using these 5 components, those are algebraic functions. Okay, so for example, you might have, say, x squared is an algebraic function. Say you can have something like the square root of 1 plus x over, say, x cubed. This is an algebraic function. Okay, then 5x squared, or maybe 5x cubed, anything like that. Any polynomial is also an algebraic function. Okay, so this LIATE rule really works very well if you have a polynomial and, say, a trigonometric function. Okay, in the integrand. Okay, you have a polynomial and, say, trigonometric, or a polynomial and an exponential function. So this rule works really well in that case. Alright, so these are all algebraic functions. Then T stands for trigonometric functions. So I assume that you are all familiar with trigonometric functions: sines, cosines, tangents, cotangents, and so on and so forth. These are all trigonometric functions. and exponential. E stands for exponential. Exponential functions. So these are all functions of type e raised to x, or maybe in the most general case you can have e to power f of x, and so on and so forth. So these are all exponential functions. Alright, so that's LIATE. So what does the exact rule say? Alright, so let's go back to our example. Now x here, x to power 1 is an algebraic function. It is of this type, and sine x is a trigonometric function, t, right? So we have algebraic and trigonometric. So look at this sequence, LIATE. Now a comes in the sequence before t, right? Algebraic functions are placed in the sequence before trigonometric functions. So I'm going to say that this guy, which is a, which happens to be before t, this guy is u, and whatever I'm left with, this part, that's going to be dv. Okay, now remember, dv will always contain dx, okay, because dv is a differential. Okay, it cannot be a simple function, so dv is always equal to sine x dx. Not always, in this particular example. Alright, okay, so that's how you apply LIATE rule. Let's see one more example where we can apply this LIATE rule. Okay, one more thing is, the LIATE rule is not identical with integration by parts. I mean, LIATE rule is a rule which helps us apply this formula. So do not get confused between the LIATE rule and integration by parts. This formula is always valid, but the LIATE rule, it's a rule we apply to facilitate this formula. Okay, so let's see one more example. Now let us have integral x e to power x dx. Integral x e to power x dx. Now what does the LIATE rule say? LIATE rule. Now this guy is an algebraic function, a, and this is exponential. Okay, so I'm going to say that this is my u, and whatever I'm left with, e to power x dx, this part is equal to dv. Okay, so I choose u to be equal to x and dv equal to e to x dx. Now I want to know what is du and I want to know what is v. Okay, so I'm going to differentiate this. So once again, du over dx gives me 1, which gives me du equal to dx. Okay, and if I integrate the second equation, I get integral dv equal to integral ex dx, which gives me v equal to e to power x. And as I said before, we are not going to add a constant of integration here. Okay, so let's try to plug everything in back into this formula. So integral x e to power x dx is equal to u times v, which gives me x times e to power x, and minus integral v du. V is e to power x times du is nothing but dx. So my final answer is x e to x minus e to x, because integral of e to power x is just e to power x, and then I'm going to add a constant plus c. Alright, so this is the final answer. Okay, all right. So as I told you, this LIATE rule and integration by parts, they work many times, but they do not always work. Okay, so I'm going to give you an example where this sort of technique does not work. I'm just going to give you two examples. We are not going to work out the details in this video, but we'll just see the examples. All right, so first example is integral, say, sine x times sine inverse x dx. Okay, it looks like a fairly simple integral. This happens to be a trigonometric function. This happens to be an inverse trigonometric function. So this is the product of two different types of elementary functions. However, if you try to apply integration by parts, it's not going to work in this case. The first step you might want to do is substitute x equal to, say, sine theta, and then simplify the integral. So you will end up with an integral of this type: cosine of sine theta d theta, and some more terms. This is not the only term, you will have some more terms, but eventually you will want to compute this sort of integral. And this is a very difficult integral to compute. You cannot do that with simple techniques. So integration by parts does not work in this case. Okay, so even if we have two different types of elementary functions, integration by parts still won't give you a simple answer. Okay, so that's first example. Second example. Okay, maybe I should change the color. Second example is, say, for example, integral x e to power x over x plus 1 squared dx. This looks like somewhat a complicated function to integrate. Okay, in this case, integration by part is going to work, but the LIATE rule does not work in this case. Okay, once again, as I said, I'm not going to show you the steps in this video, but I just want to point out that LIATE rule does not work in this case. Integration by parts does work. Alright, so LIATE rule does not work in this case. Okay, so the point is, this is a technique which works in many cases when you have two different functions of two different types. Okay, two elementary functions of different types. LIATE rule actually works very well if you have a polynomial multiplied with say, a trigonometric function, or a polynomial multiplied with an exponential function, for example. It works very well. So just remember this sequence: LIATE, L logarithmic, then I inverse trigonometric, A is algebraic, T is trigonometric, and E is exponential, and apply or try to choose U and dV according to that sequence, and integration by parts formula. Alright, so all practical purposes this is going to work, but there are examples where these things do not work. Maybe we can see some more examples next time. Alright, so that's it for today. Thank you all.